Okay, so let's go back and set the stage, okay? So first of all, where did we start? How did we start? In other words, you always ask yourself, where we are and where we are heading, where we are coming from, where we are, and where we are heading. Always. Why? Because sometimes we get a little bit. We get distracted and we start going without knowing where we are going. Okay. So, what did we do so far? Where did we start? How did we start? I'm asking you. How? Tell me. Yes? How did we start? Go ahead. Anything, say anything. Don't worry about it.
Fixed-point equations.
Oh, wallahi, I didn't hear you.
Fixed-point equations.
Fixed point equation. Yeah, that's true. Fixed point problem, fixed point equation. Yes, yes, that's true. What else? What else? Huh? Come on, tell me.
With summary of last bit. With summary of last bit.
Okay. Anyone else? What did we do? How did we start? What was it that we did? I'm talking about the beginning. Banach contraction principle. Yes? Hmm? Then what? Caristi fixed point theorem. Now, of course, if you look at the extensions of Banach contraction principle, there are many extensions. But I gave you the most beautiful one of them to learn something from it. Not we want to learn the technicalities, no. That wasn't the point, okay? You can do a better job, I have no doubt about it. So it's not the issue of technicalities. It's the issue of what was behind it, the story behind it, how it moved the area into something big, which is the echelon variation principle, okay? What else? Ran and Rurings. And what was that? Under what umbrella? Ran and Rurings.
Partial order.
Yes, but what is it? I mean, partial order is more general, but what is it? Very important.
Solution of matrix equation.
No. Anybody else? That was yesterday.
Bridge between metric spaces and graphs.
I didn't hear you.
Bridges between metric spaces and the graph.
You're good. Anybody else? What was the idea behind Ran and Rurings? It's very important. Huh? I didn't hear you.
Lower bounded.
Anybody else? That's technical. That's technical. What is it?
Focusing on all the set, we have small set inside that, only few are working.
Oh, I like that. No. I really like that. Yeah. That was the relationship. Remember the Kirk's problem? Compared to Caristi. When we put the function eta and it's not good, the relation everywhere, but it's on a small area, that's what he's talking about. Anybody else?
Comparable.
I didn't hear. No.
So matrix equation for monotone maps.
Say it again, say it again.
So matrix equation for monotone maps.
So the key word here is monotone mappings. So it was more about monotone Lipschitzian mapping. That's a concept that is new. We did not know this before, which is you have a metric space with a partial order, and you have between every two comparable elements, the function is a contraction. So it's monotone Lipschitzian mapping. Okay? So Banach contraction principle, Lipschitzian mapping with constant less than 1. Yes? This one is not on the entire space, only on the comparable elements. Are we in? And then what? How? Tell us. So in other words, we replace what? The partial order by what? A graph. So we are merging what? Now, analysis with graph theory. Do you remember? So now you have it a little bit clear what's going on. But we focus mainly on contraction. Yes? And the problem with contraction is that there is only almost one technique. One. Not two, one. What technique is that? Good job. You are really, I wish I had your energy yesterday. Good job. So indeed, there is only one technique, which is the iteration. Okay? Now we are going to be moving to something that is extremely difficult compared to contractions. Okay? Extremely difficult. And that's why people tend not to get close. They don't like it. It's very difficult. But if you miss it, because it's easier to do what? Contractions, you are blind. You are seeing only a small window. Okay? You are missing the big picture. Are we ready? Are we ready? Okay, so let's do it. So I started yesterday, which is what? Which is what happened when k is equal to what? 1. Somebody was asking me about k bigger than 1, and this was done. The only problem with k bigger than 1 is that we need to be careful. Why? Because now the distance between t of x and t of y can be bigger than the distance between x and y. Okay? Can be bigger. Expansive mappings. And therefore, there is a risk of what? Becoming what? Expanding and becoming what? Unbounded. So that's the idea. So they have what's known, to avoid this, they have what's known as uniformly Lipschitzian mapping. Uniformly Lipschitzian mapping. I will not be talking about this. Okay, I will not be talking about this. Okay. Muhammad, is it working?
Yes.
It's not working. Okay. So non-expansive mappings. Okay, k equal to 1. And as I told you yesterday, I explained it. Naturally, on a metric space, it's easy to build a counterexample, even if the metric space is compact. Okay, very easy. But if you start to put convexity, you can approximate. That's the reason why. Okay, you can approximate the non-expansive mapping by contractions. And therefore, you can use what? You can use the Banach contraction principle to have a fixed point. There is a lot written about this. What is the behavior? Because it's not just, you can find a curve in the metric space. Epsilon, x epsilon, the fixed point. So this was done. People did work on this, okay? But I'm going to move on. So what's important about non-expansive mapping in a convex setting is that you have that minimal displacement equal to what? To 0. And there are some people, including Goebel and his students, they worked on the minimal displacement, okay, for some mappings. How do you find the minimal displacement? But let's move on. That's not what I want to. Okay, so here the main questions are, under what assumptions, whether on the domain, on the map, can we secure a fixed point? Okay, that's the idea. Okay, so this is old. This is not 1965. This is old. From the beginning, they asked this question, but they couldn't. They couldn't do except under strict conditions. Like, for example, the epsilon approximation was known. No, was known. Okay. Okay. So the focus, more and more people wanted to work in the linear case. And why is that? For the reason of that what? convexity. Huh? Therefore, if I have a convexity, I don't need to be in a Banach space. Yes? Are you with me? If I can do epsilon times z plus 1 minus epsilon times t of x, if I can do this, then, okay, this is the case with what? With some metric spaces known as hyperbolic metric spaces. Okay? So for example, sphere where you have segments like cut zero spaces, etc., etc. So we do have the convex combination. We don't have linearity, but we do have convex combination. We can do the same. Okay? But at that time, they did not know about this. They were just doing it in the linear case, okay? Because they didn't know what to do. Okay, so this is what I told you. And as I said, if you look at epsilon positive 0, 1, epsilon positive, so epsilon gives me x epsilon. Yes? So this is a curve. What are the properties of this curve? Some people did this. Old, before 1965. Huh? Okay, so the first result known before is the fact that the infimum, which is the minimal displacement, so the minimal displacement is equal to what? The minimal displacement, this is the minimal displacement, is equal to what? To 0. In fact, if you have a fixed point, the minimal displacement is equal to 0. Now the question is, if the minimal displacement is equal to 0, do we have a fixed point? In other words, the infimum becomes what? Becomes what? The minimum. The infimum becomes the minimum. Huh? If it is a minimum, it means you can achieve that infimum at certain point. Since it's equal to 0, that point is a fixed point. So now if you are in a compact convex set, that infimum becomes the minimum, and you have fixed point. But why do you want to do this if it is compact and T being Lipschitzian is continuous? Therefore, we can use, and it's convex K, the domain is convex, we can use Brouwer fixed point theorem, and we have fixed point. The problem is if you have compactness, but T is not continuous for that topology. If it is continuous for that topology, okay, then you have to be careful not to fall under what? Under Brouwer's fixed point theorem, okay? Huh? You will see why I'm talking about this. Huh? So here, what do we have? Basically, we have the existence of such sequence. And we call it an approximate fixed point sequence. Approximate fixed point sequence. So, if T is non-expansive, if the domain is convex, closed and bounded, then we do have what? Approximate fixed point sequence. We don't know if we have fixed point, but we do have approximate fixed point sequence. Very important. So this is the minimal displacement. Okay, so now, what did I say just now? I said if the domain is compact and T is continuous for that same topology for which the domain is compact, then you risk to fall under Brouwer's fixed point theorem and you have fixed point. In fact, you don't need non-expansiveness. You just need to be continuous. Now, what happened in a Banach space? In a Banach space, you have two natural topologies, which is the norm topology or the strong topology and the weak topology. And therefore, when you are Lipschitzian, you are continuous for the norm topology. You are not necessarily continuous for the weak topology. So basically, you can be weakly compact, and T is non-expansive and this will not apply to our friend Brouwer. You understand? Okay? So, why at the beginning they looked at the problem from this angle? Because if the space is reflexive, then in this case, bounded, closed, convex sets are basically weakly compact. Okay? And that's why the domain weakly compact is something that's natural in the reflexive case. Okay? Because they didn't know anything. Okay? When do we have fixed point? So even if you have an approximate fixed point sequence, you will find a subsequence which converges weakly. And even if you have a convergence weakly, there is nothing you can do because T is not weakly continuous. It is norm continuous. Are you following me now? Because this discussion was ongoing prior to 1965. Okay? It was ongoing. Okay, so this, in fact, is the fixed point problem in Banach spaces. Okay, what you see there in the box, that is exactly the fixed point problem in Banach spaces. And some people will call it, including myself, the FPP or fixed point property in Banach spaces. Okay, so basically, okay. So now, 1965, the main revolution of 1965. Okay? Yesterday, I was not feeling well at night, and these guys came to bother me with Javid, and I couldn't find the information. I wanted really to look for the information for you, but I couldn't find it. You will see in a second why. Okay? I'm saying this. So maybe before I leave, I will find it. So, 3 names: Browder, Good, and Kirk. Browder and Kirk, they were in the States, and Good was in Holland, Dutchland. I consider Good to be the one who did it. Okay? Meaning he set the stage for what's going to come after 1965. So let's move on. So here we are. So we have what? The first result. This was done in Hilbert space. So again, Hilbert space is reflexive. Therefore, when we say convex closed bounded domain, it's the same as weakly compact. Okay? So Browder, while he's looking at a differential equation, okay, he needed to find a solution to an operator. Okay? So he looked at the properties of that operator, and he used, without knowing, a property that is non-expansive but not fully non-expansive. Okay? Non-expansive is weaker. He had a stronger property. Okay? But if you look at his proof, and you just assume non-expansiveness, it works. But it wasn't like looking for a fixed point. He was interested to find the solution to a differential equation. Are we in? Huh? That's what he was looking for. Right after that, okay, right after that, I forgot this. If you're convex in Hilbert, very interesting. Let me show you this. This is very, very interesting because this has something to do with hyperconvexity, okay, and ANR. So here is your convex. Okay. So it is what? Closed and bounded. Convex, closed, and bounded. Since it is closed and bounded, it sits inside a ball. Yes? So, in a Hilbert space, the projection okay, R. So for any x, Okay, if you take the orthogonal projection on K, it is non-expansive. Yes? So what you do, if you have a map, so this is K. If you have a map that is non-expansive, then you take a B, a ball, okay? And then the B, you send it to K by R, and you compose R and T. So if you compose R and T, which is T, R, yes? This TR goes from B to K, yes? So what happened, and of course K is inside B. So basically, this can be seen as going from B to B, yes? So if you have a fixed point, what happened? Okay? So the fixed point must be where? In K. And if the fixed point is in K, R of x is x. So basically what you have here is T of x equal x. Okay? So our friend Browder did not do it for any closed bounded convex set. He did it for balls. Okay? From a ball to a ball, but in fact, once you have it, then you have it for, because of the retract property, okay? This is very interesting property. Okay. Good. Good is really interesting. Good did not have a differential equation. That's why I consider him as the founding fathers of the modern metric fixed point theory for non-expansive mappings. He didn't look at what? Differential equation, nothing, nothing. His paper has nothing to do. His paper is about fixed point, pure. You have a map, and I'm looking for a fixed point. It's like Banach contraction principle is about a fixed point of a map. Nothing to do with what? Of course, we can apply it, but it's not motivated by specific problem. Okay? Now, I wanted to understand in mathematics how a theory develops. Okay? This is metaphysical discussion. No? So at the beginning, we start with some needs like geometry, distances, architects, they wanted to build things. So at the beginning, we are more motivated by developing tools. But then, the moment you start to ask specific questions on these tools and what, not on what you can do and how to use them, but by themselves, by their nature, you start to think in terms of developing a new theory. So this paper of Good, in fact, is maybe the first one that he started looking at what? At the problem of finding, or the fixed point problem. The moment you start looking at the fixed point problem by itself, nothing, no motivation, then you are putting the seeds to develop what will become the theory of fixed points. Are you with me? And this happened with topology. It happened with many things, like, for example, set theory and so on. They were never theories before. They were just tools that they needed. So, what is the setting? The setting is already there. Okay? It's not like he came up with new setting. But what he did, the way he put this together, that was something that we will be carrying for the following 20 to 30 years. Okay? So, remember, what did we know before? We know that we can find an approximate what? An approximate fixed point sequence. Now the idea is, how can I chase a fixed point from the approximate fixed point sequence? So as I told you, if the space is reflexive, okay, or you have weak compactness, then there is a subsequence which converges. That subsequence converges, the weak point will be a fixed point if you have something that's called Opel property, okay? So yes, by the way, Opel came a little bit after 1965, but my point is, how can you chase the fixed point? That's the idea. How can we pick or find the fixed point from the approximate fixed point sequence? And what he did is what's known as the asymptotic center. So you start with your sequence and you look at the asymptotic center. If you are uniformly convex, which is old, 1936, from Clarkson. If you are uniformly convex, they knew that the sequence will have one asymptotic center. I'll tell you what is asymptotic center. So what he proved, in fact, is what? That asymptotic center, X, asymptotic center of the sequence Xn, because it's an approximate fixed point sequence, T of X is also an approximate fixed point center. And therefore, what happened? The asymptotic center uniqueness will give me what? T of X equal to X. In the case of Opel, the center, or the asymptotic center, is exactly the weak limit. In the case of Opel, if you have the Opel property, then the asymptotic center is exactly the weak limit, okay? The weak limit. So you need geometry for you to be able to conclude. Okay, now, this is a property that was known as regularity of, so when you take half the identity plus half t, okay, half the identity plus half t, and you take the iteration, okay, so this is known as Krasnodębski, Mann, Ishikawa, okay, iteration. And what is interesting about it, it generates an approximate fixed point sequence. It's very interesting. So you have a constructive way of generating an approximate fixed point sequence. So remember, before I gave you the approximate fixed point sequence through what? Through Banach contraction principle. So we do have one. But to build one, you need a little bit more, and this is a way of how to do it. It's a little bit technical, but not really profoundly technical, okay? Now we have this concept of asymptotic center, and finally, the weak compactness, okay? So all these ingredients were used in the paper by Good, and these ingredients are the ones that we developed over the years after his publication, after 1965. Okay, so here is the theorem. It says what? It says that if you have in a uniformly convex Banach space, and if you have a bounded closed convex subset, and T non-expansive, you have fixed points. Okay? So this is similar to what? To Browder, except the setting. One is uniformly convex, and the other one is Hilbert. Hilbert is uniformly convex. Hilbert is uniformly convex. Okay. Right after that, Browder went back and he revised his what? His paper. Same year. I'll tell you what I was looking for yesterday. So here he went back and he published this paper where is the same conclusion as what? As Browder. But the technique is different. And it caught my attention yesterday. And I wanted to check something because Browder is very famous for not being honest about prior knowledge. He will not mention any prior knowledge. Anyway, I wanted to go back to find the date of submission, okay? And if you don't find the date of submission at that time, something is fishy, it's not normal. Okay. but it's the same. The proof is totally different, okay? And I will say something about it. Okay, so how did he approach it? So now I told you about Browder, yes? Sorry, about good. Good, it was this iteration of the half identity plus half t, okay? And he constructed the approximate fixed point sequence through that iteration. Not him, it was known before, okay? But he used it, okay? And then the asymptotic center, okay? And he showed that the asymptotic center is a fixed point. That's how he did it, okay? In a uniformly convex, the asymptotic center is unique. Very important. It's unique, not in general. First of all, you have it because of reflexivity. Follow all this, because we don't want to miss any assumption. You do have an asymptotic center because you want to achieve the minimum, the infimum of something, okay? So you need reflexivity, number one. Number two, uniform convexity tells you there is only one. Okay, the uniqueness of the asymptotic center. And since x and t of x, if x is the asymptotic center, t of x will be also asymptotic center because the sequence is approximate fixed point sequence. For Browder's second paper, this is totally different. Okay? So you have now, this is what I want you to pay attention to. You have t, which goes from k to k. Yes? So k is invariant because t goes from k to k. So you look at all the convex subsets closed of k, which are t invariant. And then, by inclusion, you can use Zorn lemma to have minimal convex sets. So they do exist. Minimal, convex, invariant sets. Convex, closed, and they are all bounded because of k. Great. What did we use here for the existence of the minimal? What did we use? We used the weak compactness. Why? To apply Zorn lemma, you want to show that any chain, okay, has a lower bound. So if you take the intersection, not empty, then it will be what? A lower bound. That's why. Now, the beauty is, what are the properties of the minimal element? Why? Because we want to show that the minimal set is 1 point. Because if it is reduced to 1 point, singleton, it will be a fixed point. See? That's, you're chasing your fixed point this way. So what did he do? He took that minimal one and he built one that is smaller. Okay? He built one that is smaller. How? It's very important. How did he do it? He said, okay, either we have 1 point and the job is over, or we have more than 1 point. Either we have 1 point or more than 1 point. How do I know how to characterize that you have 1 point or more than 1 point? Is by looking at the diameter. Either the diameter is equal to what? 0, or the diameter is what? Positive. So if you have a diameter that is positive, he used uniform convexity to what? To reduce the diameter. So the set you are generating is smaller. It has a smaller diameter. Are you with me? Huh? And then, of course, if you build another set inside that one that is minimal, T invariant, then you get a contradiction, and therefore that diameter of the minimal one is 0, which means you have fixed point. These are the ingredients. What caught my attention is that these are exactly the ingredients of Kirk's fixed point theorem. And this is what really yesterday caught my attention. And then I started looking, before Izhar and Javid came, started looking when was it submitted, that paper. And I did not find it yet. Okay, so let's move on. It's totally different from good, yes? I told you, huh? Good approach, and this approach which is similar to Kirk's approach. Okay, so this is what I was telling you. And now we go to our friend Kirk. Same year. 3 papers, or 4 papers if you want. I always ignore the first one, because it's very technical to a differential equation. So 3 papers. They set the stage for the development of the theory of fixed point for non-expansive mapping. Okay? So now we go to our friend Kirk. Same year. So what happened? Kirk was was a geometer, was not fixed point theorist. There was no such thing as fixed point theorist anyway. So he did his PhD in geometry, and he was doing geometry, pure geometry, with a famous mathematician, by the way. And he came across a paper. I don't know, you are too young to know this. Russian publications in the old days, I'm talking about in the 80s and earlier, 60s, 70s, 50s, what they used to do in the old days, 30s, 20s, Russians, they were publishing in French because the aristocrats in Russia, they spoke French, not Russian. So the intellectuals in Russia, they were speaking and writing in French. But after the Bolshevik Revolution, they started to write, because of their national identity, in Russian. The problem, the Russian language, which was the masses language, is not commonly known, okay? And therefore, they wrote in Russian, but not that many people read their work. So this paper was written in 1948 in Russian. And what the Americans will do, they did not translate all the Russian publications, but they put the abstract and the theorems in English. So you will find a volume with all the Russian publications that came, for example, in a quarter, like 3 months time interval, and they will put the abstract. You can find them in the library. I'm pretty sure you can find them in the library, where you have the abstracts, the authors, the journal, as well as the main theorem of the paper in English. Okay? So Art found this paper by Brodsky and Millman, where you have geometric property. Geometric property. I told you that he was a geometer, okay? Geometric property where the convex set has a point that all the group of isometries acting on the set, they leave invariant. That point stays invariant by all isometries acting on the set. In terminology that is modern to us, it means that point is a common fixed point for all isometries. Yes? That's what it means. So Art was interested to understand how, what is this geometry, okay, this property, and how the proof. But he couldn't understand it because it was in Russian, the paper. So what do we do when you don't know Russian or any other language? Like Javid was asking about good paper. He thought it was written in German, but it was written in Dutch. Send it to him. What do you do when you have a paper that is not in your native language or your language or even a language that you know? What do you do, mathematically speaking? What do you do? Tell me. I'm just curious whether what Art did is natural and normal. That's why I'm asking you. I'll tell you afterward why I know this. But anyway, tell me. What would you do if I give you a paper in Russian, mathematical paper in Russian? What would you do?
We will just look at the equations.
That's exactly what he did. That is exactly what he did. And I am glad and thankful to God that he did that. Wallahi, I am glad he did that. Why? Because if he knew Russian, if he translated the paper, he would have stayed with that property and geometry. That's it. But because he just took the math and he ignored the text, yes? When he did that, he discovered by putting the stuff together, trying to understand, putting the stuff together, step from step from step, that in fact he does not need an isometry. So he starts with one map. So instead of proving, which is the center, the Chebyshev center, so what he did, he worked with one map, and then he came up that there is a point that is invariant by that map. So in other words, he does not need, in his calculations, T to be in isometry. So what does he need? He just needs norm of Tx minus Ty less than the norm of x minus y. Meaning what? Meaning what for us? Now, it means what? Non-expansive. His paper does not talk about non-expansive. He talks about a map that do not increase the distance. That's exactly the title. Because there was no non-expansive at that time. So how do I know about this story? Because we were in Chile, me and Art, and we were having dinner, and he was relaxed, and we start talking about stories, including Karisti and so on and so forth. And I asked him about this theorem, so that's why. And he told me the story behind it. Okay, so what is now normal structure property? Okay, so this is it. So this is the property of Brodsky and Millman. And this is what he discovered by looking at the math, not the translation of the whole paper. If he did, I assure you, we would never have seen this theorem. Never. Because who wants to look at normal structure? For us, people working in Banach spaces, in fact, Browder, he used what? Uniform convexity. That was commonly known in Banach spaces, not normal structure property. Okay? You see the theorem, a fixed point theorem for mappings which do not increase distances. Do not increase distances. So again, if you have a bound closed or convex subset of a reflexive Banach space, okay, reflexive Banach space, and why is that? Why? Because he wanted to have weak compactness. Yes. So it's enough to assume that K is what? Weakly compact. We don't need the space to be what? Reflexive. But this refinement came afterward. At the beginning, he was so proud of himself, so happy to prove this theorem, he didn't care about optimizing the assumptions. I know only one mathematician who is amazing in optimizing. He will never publish a paper till he optimizes the assumptions in his paper. If you change anything in the theorem, you will find a counterexample. And his name is Pekilin. Okay, let's move on. And the reason why, because I was told, don't try. I was working on his papers when I started my PhD, and they told me, be careful about this guy, okay? Okay, I'll come back to the normal structure property, but let's go to uniform convexity now, okay? I want to go to uniform convexity. So what do we know? This is our friend, what's his name? Clarkson, okay? So you have the parallelogram identity. Everybody knows the parallelogram identity, yes? So what happens if you divide by 4? If you divide by 4 here, you get what? X plus y over 2, x minus y over 2, and 1/2, yes? So what is the geometric meaning of this? So this is, I'll show you this way now. What does it mean? It means that if you have a ball and you have x and y. And you have the distance between x to y, which is bigger than epsilon. So in other words, they are a little bit far from each other. The middle point will be where? Will be inside. That's what it means. If the middle point is not on the sphere, this is known as strict convexity. You cannot have a segment on the sphere. But to be inside with the control, there is a distance there between the surface and the middle point, that is uniform convexity. That is exactly uniform convexity. Now, you have it there. If the norm of x minus y is bigger than epsilon, what's going to happen here? So remember, there was a 2 here, yes? There is a mistake here. It should be epsilon over 2 squared over 4. So this will be less than 1. This will be less than 1. 1 half, 1 half. Remember, there was a half, yes? Because I divide by 4. So this will be less than 1. 1 plus 1 over 2, 1. Minus this is bigger than this over 2. So to find this, you take the square root, yes? You see it, huh? So you have a control. And this control is less than 1, yes? Yes? How far you are from the surface? How far? So this is how far is this distance? What I gave you is this distance. How far is this distance? Huh? 1 minus that. Do you agree? 1 minus that number. That number, 1 minus that number, you see the distance, that's known as the modulus of uniform convexity of the Banach space, delta of epsilon. Okay? That's the distance. So what you have here is, here you have 1 minus delta, and here delta. So this is delta. And here you have 1 minus delta. Okay? Of course, this is in Hilbert. Huh? So you can do exactly the same, and that's what Clarkson did, in any Banach space. Okay? So here is the definition that he offered in 1930-something. Okay, Clarkson, 1936. Sorry, because I tried, my AI assistant gave up on me yesterday. I tried to, the reference is hidden under this definition. I have the reference, yeah. Okay, so you see it now. Huh? The norm of the middle one is less or equal than 1 minus delta, yes? Huh? Huh? So uniform convexity means what? The delta is not equal to 0, yes? Because if delta is equal to 0, then we are going all the way to what? To the sphere. Okay, let's change it, and you will understand in a second why. Because there is something big behind all this. Let's change it from norm 1 to norm R. Are we in? Norm 1 to norm R. In other words, I'm looking at the sphere centered not anymore at 0, at certain points. Okay? So as you can see, here in this picture, I did not say we have 0 here as the center. I can say any point. And now I change this into radius r. And the distance between x and y, I can say, is bigger than r. small r. Okay, the distance is bigger than small r. So what will be your epsilon? So I mean, just putting stuff together. It's not really big deal. You will understand in a second why. But it's how can I now work not anymore in the unit ball centered at 0. Because we are in a Banach space, it's the same. But there is a reason why I want to do this. So you see, here it is, where I shifted everything to what? To a ball with center P and radius R, capital R. And now the distance between x and y is bigger than little r. Okay? And I mean, of course, the little r is less or equal than 2r. Yes? Because of the triangle inequality. Yeah? So if x minus y is greater than r, this is less or equal than 2r. Yes? Therefore, the little r is connected what? To capital R. Okay. This is very interesting. Why? Because it prepares me to go to the definition for uniformly convex metric spaces. You see where I'm heading? So I have the definition in Banach spaces, and I would like to define this in metric spaces. So I call it the nonlinear version of uniform convexity. But wait a minute, wait a minute. What do you mean by x plus y over 2? Okay? So in order for you to take it to metric spaces, you need to have the concept of middle point. Once you have the concept of middle point, then you can define this, no problem. You replace the norm by what? By distance. Now let's go to 0. Why I moved from 0. All this took me years to think of it. Wallahi, years to think of it. So let me take you now, and you will see the definition of UCID. I had to come up with a new definition equivalent because to adapt it to metric spaces. So for example, if you look at the one before, look at this. Norm of x, norm of y. What is norm of x? In fact, norm of x is the distance between what and what? Between 0 and? But in this case, I need a 0. What if I am in a metric space?
Middle point of the distance.
If I am in a metric space? If I am in a metric space, I don't have a 0. 0 is what? The vector that is neutral to the addition of the vector. Yes? But in a metric space, I don't have that. I have what? I may have the middle point. It doesn't mean I have a 0. And that's why I moved to what? To another center. Because now I can say what? Is the distance from what to what? Is the distance from what to what? From x to what? To p. Do you understand now? Is to adapt it to the nonlinear what? Structures. Now the question is, do we have nice nonlinear structures with the middle point concept? Do we? Hyperbolic spaces, cut zero spaces, and so on and so forth. Okay? So we do have non-trivial books are written. If you go to Javid's office, you will see it on his desk, a book dedicated to metric spaces where you have it's not the only one. You have another one by Goebel and Shimon and others. Okay. Now, uniform convexity. Uniform convexity, this is James, by the way. Uniform convexity is for every epsilon between 0 and 2. For every epsilon between 0 and 2, you have delta of epsilon. Okay? That's the definition. Okay? And delta has some nice properties, including that is an increasing function. But what if delta is 0 at the beginning? So let me do it here. So epsilon is defined on 0, 2. So the uniform convexity tells you you have something like this, increasing and non-zero for, of course, 1 is the biggest value. This is delta epsilon. Okay? But what if I am equal to 0 here, and then I take off? Allowing ourselves to be equal to what? To 0 at the beginning. So you are no longer what? You are no longer uniformly what? Convex. So this number here that you see, this number, has a name. We call it the characteristic of convexity of the Banach space, huh? That number. Okay? That number has two options. Either it's less than 1 or bigger than 1. If it's less than 1, it's beautiful for fixed point theory. If it's bigger than 1, it's beautiful for, but not 2. It's beautiful for the geometry of Banach spaces. That was James who did it. Less than 1, us, we did it. Less than 2, he did it. For the geometry of Banach spaces, it means that you don't have a square on the surface, because you have segments now. If it's equal to 0, some epsilon, it means you have segments. So they call them non-square Banach spaces. Non-square Banach spaces. Okay? So when are we uniformly convex? If the characteristic is equal to 0. Okay. So this is, I want just to show you all these geometric properties of Banach spaces. Huh? This is old, by the way. It's not like 1965, no. Okay. Strict convexity, what does it mean? You don't have segment on the sphere. Okay? Segment. Now, this property, strict convexity, and this property are similar. You should see them. This property and this property are similar. One is uniform of the other one. Okay? So R, capital R, is this number here. This one and this one. That's R. And this one is R. This must be equal to 0. Okay? So it's some kind of uniform strict convexity. So for some of you, they may not know, if you go to the ultra power of the Banach space, this is telling me exactly that ultra power is strictly convex. That's what it says. So it can be written in this form. Okay. I'm showing it to you because this will be important. That's why. Again, if I want to have this property in metric spaces, what happens? I will have to shift from xn to xn minus p. Do you understand? Huh? So we can adapt it to metric spaces. Okay. Now, in a uniformly convex, what happened? Convex sets are proximal. Strict convexity tells you that you have at most one point, the projection of x on C. Okay, you have at most one. That's strict convexity. But uniform convexity assures you there is one. You see the difference? With strict convexity, you may not know if you have a projection. Okay? But in the case of uniform convexity, then you do have what? A projection. Since you are strictly convex, it is unique. Right? Or if you want, the projection is single valued, not multi-valued. Now, how do we prove this? Very easy, from the theorem before. Why? Because, okay, it's an infimum. Yes? What did they write here? Ah, okay, there exists y, yes? Y is unique. So anyway, so let me show you how to do it. You take Zn, a sequence in C, such that this distance goes to the infimum. Okay? So what's what we call an approximate sequence. You are approximating the distance, yeah? And this Zn is Cauchy. That's uniform convexity. Okay? And since it is Cauchy, it converges to this one. You got it? So you assume it's not Cauchy, and what does that mean that is not Cauchy? It means Zn minus Zm will be bigger than what? Epsilon. That's part of the definition of uniform convexity. Are you with me now? Huh? And you will find that Zn plus Zm over 2 gets closer to x. Anyway, so that's number one, property fundamental. Okay? Property number two, if you take a family of bounded closed convex sets that is nested going down, their intersection is not empty. If you remove bounded, it's false. All right? Because you can take the closed intervals on R, 1 to infinity, 2 to infinity, 3 to infinity, their intersection will be empty. Are we in? Okay. So if it's bounded, these closed intervals, convex sets that are nested going down, the intersection is not empty. Okay. That property, according to Shmulian, that property gives me exactly reflexivity. Okay? Now, this is very important when people, after the publication of Kirk's theorem, they wanted to have Kirk in metric spaces. Okay? The theorem of Kirk, you need weak compactness. So the question was, what is weak compactness? This is very important. You will not find it anywhere. What I'm telling you, you will not find it. It's not written. So let me rephrase what I'm saying. Kirk's theorem says what? If you have weak compactness, convex, weakly compact, and you have non-expansive mapping and normal structure property, T has a fixed point. This is Kirk's theorem. So what is this theorem in metric spaces? So first of all, I need a convex. Yes? So a convex, if you have x and y, you can have x plus y over 2. Yes? Yes? That's one way. That's Takahashi's way. But there is a guy, he came with a totally different what? Approach. And he called it a fixed point theorem without convexity. That's exactly how he called it. His name is Penaud, French mathematician. And how did he do it? I wanted to listen to this carefully. There is a book written on this in economics. So he used the concept of convexity structures. So what is a convexity structure? Hey, what do I know about convex sets? Well, I know that the intersection of two convex is convex. In fact, the intersection of any family of convex sets is, you know what? I take a family of sets and I put this condition on it, and that's my family of convex sets. Now, what's interesting about this definition, and there is a book, I have it by the way, about convexity structures, it works in discrete sets. It's set theoretical approach of convexity. And now, imagine all what you can do. The door opens into something big, meaning what? What is a convex function? Every x, every r, the set of x for which phi of x is less than r is convex. If I know I have my family of convex sets, it means it belongs to the family. Of course, you do not have what? X plus y over 2. Because you have now a definition of convexity. Yeah? You have no idea how profound this changed our view of Kirk fixed point theory. Do you remember yesterday I told you about Tarski? Yes? What was Tarski? Does anybody remember? I'm just testing you. What does Tarski say?
Order preserving map
Order preserving map, monotone,
as a fixed point.
On a complete lattice.
on a complete lattice. Guess what? This is Kirk's theorem. This theorem is exactly Kirk's theorem. Do you remember Poussey? Does anybody remember Poussey? You don't remember, huh? Yeah, I gave you so much. Yeah, I'm sorry. I'm very sorry. Do you remember the discussion about finding a more general definition of a distance? Where distance from x to y less than r for the balls, it becomes x and y belongs to the relation r. Do you remember this? So the group of Poussey at Lyon was exactly working on showing the people that Tarski fixed point theorem is exactly Kirk's theorem. So let's move on. The reason, again, I'm saying all this, it opens your view of things. You do not just look at it in a narrow way. You start to look at it, what? You open up. And once you open up, sometimes you end up seeing things that are unconnected to be what? Connected. Let's continue. Okay, this is important. Now, what do? We take this function. People working in geometry of Banach spaces, they call it type, okay? For what's known as stable Banach spaces. Stable Banach spaces, okay? Is a terminology that you can find because they have something very nice, what we call the spreading models of a Banach space. I worked on this at the beginning because I was in Banach space geometry. I was not in fixed point theory. So what you see there, the tau there, is what's known as a type in Banach spaces. But in the people who are working in fixed point theory, they call it the asymptotic center of xn. So this function is associated to xn, this function tau, and then you are interested to find the infimum, okay? Where you achieve the infimum. That is the asymptotic center. So you are looking at the infimum of tau, and you're looking at the point where tau achieves its infimum, the minimum point. We call them asymptotic center of the sequence xn. Are you with me? Now, don't worry about names. It's not important. Wallahi, it's not important. Now, focus. Now, what if xn, let me give you two examples. Xn is approximate fixed point sequence, okay? Think, approximate fixed point sequence. Since xn minus t of xn goes where? 0, I can replace xn by t of xn, yes or no? Huh? Now, tau of tx, tau of tx, this becomes t of xn, t of x. But t is what? Non-expansive. Therefore, less or equal than what? Norm of xn minus x with limit tau of, therefore tau of tx is less than tau of, therefore if I have a minimum point, x, t of x will be also what? A minimum point, meaning if x is a center, asymptotic center of the sequence, t of x will also be what? So we have two problems. Number one, do I have a minimum asymptotic center? Number one. Number two, do I have one or more than one? If I have tool that allows me to say, number one, that I do have a center, perfect. Tools that you don't have more than one, I won. You understand now? Do you see it? That is exactly what good did. Exactly. Reflexivity gave you the existence of a minimum. And uniform convexity gives you the uniqueness. From that famous theorem I told you, which is uniform version of strict convexity. Do you remember? You got it, huh? Without going to technicalities, huh? That's what I was just saying right now. Okay. Now, I told you if xn is what? If xn is what? Approximate fixed point sequence. But there is another one that is a lot easier, which is Tn of x, any x, take the orbit, and generate the type of that sequence. Yeah? So think of it now as you have Tn of x0, Tn of x0. Now what is tau of Tx? It's going to be Tn of x0 minus T of x. Again, T is non-expansive, less or equal than what? Tn minus 1 of x0 minus x. But lim sup of Tn or Tn minus 1 is the same. Therefore, tau of Tx will be less than tau of x. So there are two ways you can do it. Either by what? Taking approximate fixed point sequence, or taking the orbit. Now you tell me. Now I'm testing you. Do you remember the famous test about what made Banach contraction principle famous? I have a test for you. Why these two ways are important? So one, I'm using what? Approximate fixed point sequence. And the other one, I'm using the orbit. Why these two are very interesting and not to be ignored? Tell me. I'm just curious. So both of them will lead to the same result, but differently. Because one uses approximate fixed point sequence and the other one uses what? The orbit. Why both of them are important? Tell me. And as I told you before, we are among friends. You can say whatever you want. Don't worry, but don't be shy.
The latter one gives the guarantee of fixed point in partial order state.
Keep in mind, I'm looking at the distance. Yes? What you see there is the distance between xn and x. So I must have distance. So it's not enough to have only what? Some partial order. You need to have a distance. Anybody else?
I think orbitals may have fixed point for some n.
No. Anybody else? It's a really beautiful question. So you want me to rephrase the question? I can rephrase the question. You want me to rephrase the question? So I just showed you what? That either you have xn, which is what? Approximate fixed point sequence, or the orbit. Huh? It will lead to a fixed point by looking at what? At the asymptotic center, or the minimum. Okay? The two of them are different in nature, but they are fundamental, both. Why is that?
Yesterday we were looking on a circle, the rotations, theta rotation, that doesn't have fixed point. But
No.
if theta is rational, we can at some orbit, at some n, it may have fixed point.
I like what you're saying, honestly. I really do. So, very simple. What do you see there? What do you see here? Here, what do you see here? What do you see here? This. What is this? No. Distance. Between what and what? That's what we do in metric spaces. This concept of type is well defined in metric spaces. But you see, in a metric space, I can work with the orbit. I cannot work with approximate fixed point sequence. Because the existence of an approximate fixed point sequence is ensured in a convex set in the Banach spaces. So I may not have what? I may not have in the nonlinear structures, I may not have an approximate fixed point sequence. If I have it, perfect, but I may not. But the orbit, I can. Do you see now? So if I have a means in metric spaces to ensure what? There is an asymptotic center, and it's unique. Hey, we made it. Through what? Through the orbit. Do you see now? So keep in mind, whenever I do something, I am keeping my eyes on different structures. So at the beginning, when I was a student, I was only looking at the asymptotic center in Banach spaces. Do you understand? But more I learn, more I get to learn, I start to connect all these concepts together. Because by connecting them all together, I get a better view where I can go in cases I am not in Banach space. Do you see what I mean? Are you with me now? Or I'm bothering you? I'm bothering you. Well, I am bothering you. Izhar, you should stop me. Come on. Okay, so let's continue. Here it is. What I just told you is right there. So whether you have an approximate fixed point sequence or you have what? An orbit, the asymptotic center will be a fixed point. You got it? That's what it means. Okay, now what is the normal structure property? Now let's go to our friend Kirk. Ready? I need your attention now. This is serious now. Why? If you remember, what did I tell you? Pay attention to what I'm saying now. This is serious now. I told you that Brodsky and Millman was looking at a property from a geometry point of view. Yes or no? That's what I told you. Huh? Kirk was looking at that paper from what point of view? Geometry point of view. Yes? That property was unknown to whom? To the people working in Banach spaces. What they knew was uniform what? Convexity. They have no clue or anything to do with what? With normal structure property. Now, if you do a search on normal structure property in Banach spaces, it started in 1965. So at the beginning, nobody knew about this property in Banach spaces. Guess what? It is the single property that is totally misunderstood till today. It's simple, but extremely difficult, and I will tell you some of the open problems about it. So here it is. So what is now the normal structure property? You take a convex, okay, and you take for any point, there are different terminology about the Chebyshev radius, but let me give you the simple ones that are interesting to us for the fixed point theory. And you look at the so we have a convex. Okay. For any point, you look at the smallest radius of a ball centered at X that contains the convex. So we have what's known as the inner and the outer. I'm working only with the inner for the fixed point property. So I'm looking at the smallest radius of a ball centered at X, which contains what? K. So if you want to find it, Rx is exactly the soup of the distance from x to y. That is exactly what it is. Okay? So the smallest ball centered at x, which contains your convex. Yes? And now you take the infimum of these radiuses, and you call it the Chebyshev radius of K. All right? The Chebyshev radius of K. Now, this Chebyshev radius, in some cases, including the Hilbert space, is going to be less than the diameter. In fact, in the Hilbert space is less or equal than square root of 2 over 2. So it's not just less. It's less than square root of 2 over 2. Okay? So this is what's known as normal structure property. Whenever you have this property, we call it what? The normal structure property. Wait a minute. What was R of K? R of K is the infimum. And you are saying that this is strictly less. When this will happen? This will happen if I can find one x such that what? See? This happens if there exists x in K such that this is less than diameter. Yes or no? Because it's the infimum, and the definition of the infimum gives me this. This is exactly this. Now, what is the not normal structure property? It fails. What does it mean? But it means that R of K, because these numbers are all less than diameter. So this less or equal is obvious. And also it's bigger than half diameter by the triangle inequality. Okay? Now, what does it mean equal? Means that every x, Rx, is equal. Yes, to the diameter. Which means that when Rx is equal to the diameter, we call it a diametral point. That x is called diametral point. So what does that mean? It means that any x in K is diametral. The normal structure property tells you that there exists an x which is not diametral. When every x is diametral, we call it diametral set. So when you have normal structure property, you do not have what? Diametral set. And if you want an example of a diametral set, you go to little L infinity and you take the unit ball. The unit ball is a diametral set. Are you in? Okay? Now, let's continue now. So these are just the definition of the Chebyshev point and so on and so forth. And where you achieve the infimum is called the Chebyshev center of the set. X such that Rx is equal to R of K is known as the Chebyshev center of the convex set. Okay? So just terminology, Now, look at this. Do you remember the characteristic less than 1? Do you remember? I told you if it's less than 2, people, James, working in geometry of Banach spaces, this is non-square Banach spaces. But if it's less than 1, it has an impact on fixed point theory. Do you remember? Here it is. If it's less than 1, the Chebyshev center, you see it, is this inequality here. There is a non-diametral point that satisfies this inequality. Epsilon is to be taken between epsilon 0 and 1. It's less than 1. Less than 1. So if you take epsilon between the two, you can find an x for which you have this inequality. What did they tell you about Hilbert? How much do I have here? Square root of 2 over 2. Huh? That's what you have right here. Are you with me? So this is beyond normal structure. Normal structure is only less. What happens when you have a number here, square root of 2 over 2, or this one? This is known as uniform normal structure property. Uniform normal structure property. Okay. Okay. What did I tell you about Browder in the second paper? I told you that there was an analogy with what? With Kirk. Yes? So he took the minimal what? Set. Do you remember the minimal set? So what's interesting about that minimal set, and that was in the paper by Kirk, he has these two, for Kirk only, he has these two properties. Property number 2 is that it is diametral. Yeah. So at any x, Rx is equal to the diameter. And property number 1 is beautiful. It's just set approach. You have K is convex. You have, it's very, very simple. And it's very important because it's set approach. You have K, T of K included in K. Yes? The minimal, the minimal. So the conv of Tk is going to be included in K because K is convex. Yes? And therefore, what is T of this? But it's going to be included in T of K. And T of K is here. So this is included in the conv. Therefore, conv of Tk is invariant. And since it is included in K, then we must have a biminimality equal. So that's why. And that inequality there is fundamental for the second property. So the property number 1 is important for the second property. Now, if you have normal structure property, what does it tell you? They only said that is diametral if the diameter is equal to what? To 0. So if the diameter is not equal to 0, you are not possible to have this. Do you see what happened? See, if you have normal structure property, that minimal set must be reduced to 1 point, therefore you have a fixed point. You see how? Of course, we want it to be non-empty. We need what? Weak compactness. So weak compactness tells you that the minimal, remember, exists and is not empty. Okay, here is the theorem. Property B is crucial, but you cannot get property B if you don't have property A. Okay? Now, I didn't have time to put more. No, I have more, but I didn't have time to tell you about, is there anything else we know about that minimal set? Every time we discover something about the minimal sets, it opens the door to something big. So we know of one more property, one more. So we have A, B, and there is one more that was discovered in 1975 by Karlovich. And Goebel claimed, which by the way, I'm one of the people who believed him, is fine, that he published it in Eastern Europe and it was not known, and he showed it to us. So now we call it Goebel-Karlovich-Lemma, after he showed us that. But for a while, we used to call it only Karlovich-Lemma. In fact, in my first papers, I was just writing Karlovich-Lemma. One tiny property about approximate fixed point sequence in the minimal set. In the minimal set. Beautiful. Let's continue. Now, we have this property. Yes? Which is a variant of a baby of uniform convexity. So we call it uniform convexity in every direction. If you go back to the original definition, you are not going to find it this way. Okay? It's equivalent, by the way. Why do I like this one? Who wants to tell me what is special about that definition? Exactly. The other one, it uses the direction. And do you know what the direction is? If you go back to the original definition, it's z1 minus z2. And the problem I have, if I am in a Banach space, I'm sorry, in a metric space, non-linear, how do I define z1 minus z2? But in the case of this definition, I have the distance from x to z1, the distance from x to z2, and the distance from x to z1 plus z2 over 2. I just need the middle point. I don't need the difference. This definition, I just used it not too long ago. It was more convenient to work with this one. They are equivalent in the case of Banach spaces, except one is good for metric spaces, the other one is not good for metric spaces. So, again, if you have UC uniformly convex in every direction, you have the normal structure property. In fact, you have more. The center cannot have more than 1 point. You only have 1 point in the center. But we don't care about what? Having 1 point. We may have more than 1 point as long as the radius, Chebyshev radius, is less than the diameter. That's the normal structure property. I'll come back to this point. So you see it? This shows you that what? That the radius is less than what? 1 minus delta times r. It depends on z1 and z2. Don't think you have what? Uniform normal structure property. You have normal structure property, yes, because z1 and z2, this delta here depends on z1 and z2, depends on the point. So if you have UC, you have normal structure what? Property, okay? But it's too strong. I'm almost done. The question became, does any reflexive Banach space have normal structure property? So do you remember what I told you about normal structure property? It's very important. I told you that it was discovered by Brodsky and Millman in 1948 and connected to to fixed point property by Kirk, pure accident. Yes or no? If you do a search on normal structure property in Banach spaces, you're only going to find things done after 1965, not before. Okay? Great. Now, this problem by James was solved after 1965. So when they asked a reflexive Banach space has normal structure property. Why? Because they thought that normal structure property is equivalent to fixed point property. They really, it took center stage because we know that uniform convexity implies UC implies normal structure property. And they thought for a while, for quite a while, that these two are equivalent. Yeah? So James told them, no. Not no. He answered the question whether a reflexive Banach space has what? Has normal structure property. It took center stage. All the research at the beginning, from 1965 to 1979, 1980, it was mostly about normal structure property. Mostly about normal structure property. And the famous paper by Zisler that I read when I started my PhD, it was about equivalent norm that are UC, uniformly convex, in every direction. That was the beginning of my thesis. Now, the example is L2. I want you to pay attention to this. The example is little L2, Hilbert. And you take an equivalent norm with 2. Do you see it there? Now, if you have this norm, it's equivalent to the norm 2. So it's an equivalent norm. the unit ball for this new norm does not have normal structure properties, it's diametral. Wait, if you take square root of 2, you don't have normal structure property. If you take anything less than square root of 2, there you have normal structure property.
What is setting norm?
Sup
Norm on
or max between norm 2 and norm infinity.
norm infinity on L2.
L2. The maximum of the x ends. Yeah. Now, I didn't write it, but I will come back in a second to this number 2. I want you now to think with beta. Remember, norm infinity is less than norm 2, and therefore this is all bigger than norm 2. But it's less than the maximum between 1 and 2. I'm sorry, 1 and beta norm 2. So beta is bigger than 1 anyway. Okay? We want to take beta bigger than 1. So this beta, these spaces, they really thought they found something. This is all James, huh? Okay? I'm almost done. I'll come back to it. So remember about the beta here. So does this one fail normal structure property, but does it have fixed point property? Why? Because for a while, really for a while, they thought that normal structure property and fixed point property are equivalent. They thought. This problem collapsed when we proved that these spaces, they have the fixed point property. So we know we fail the normal structure property for beta bigger, at least 2. That was the example given by whom? By James. But Picquelin, the famous Picquelin, proved, in fact, that for any beta, this space has the fixed point property. What's interesting about this, and they wrote a book on this, an entire book that Izhar keeps reminding me about it, dedicated to that. Entire book dedicated to that, which is non-standard what? Techniques in fixed point theory, okay? So why I'm saying this, not because I want to show you I wrote a book or this or that, no. What I want to show you is behind this is something very profound. That's what I'm trying to say. To prove it, very complicated, okay? So I'm almost done. 2 more slides and I will be done.
Yes.
Okay? Yeah? So just 2 more slides and I will be done. Okay, now I want to show you some of the problems that they are open for the last 80 years in fixed point theory, okay? Till today, okay? So the mother of all problems, okay? The mother of all problems is the one that you see there, okay? Now, if you go back to the original problem, I don't want to do it, but do you remember? If you go back to the original problem, what was the original problem? What's the difference between the one I put, the fixed point problem in Banach spaces, and this one? What's the difference? Does anybody remember? There was a box, and they told you this is the famous FPP in Banach spaces. Do you remember?
There K subpart, and here the entire space.
Exactly. In that one, K was weakly compact. I didn't say that the space is reflexive. That one was solved in 1979 by Alspach. He published 2 pages. These 2 pages, till today, people don't understand them. Braley-Sims. Do you remember my first talk with Ziad and Braley-Sims and G-metric spaces? He wrote a book to explain the 2 pages. The problem of finding a weakly compact and a map T till today is still people are looking for it. A simple example. And that simple example is related to what you see there. Does any reflexive Banach space have the fixed point property? This is the mother of all problems in fixed point theory. Now, one of the biggest mathematicians in France, his name is Moret, okay? And I worked with him when I was doing my PhD. He's the one, after Alspach found a weakly compact convex subset in capital L1. And what he showed them, reflexive subspaces of capital L1, they have the fixed point property. So it's almost a positive answer. Not fully, almost positive answer. He's the one who did introduce non-standard techniques in fixed point theory, 1979. The book was based on Moret's work. So that's the first one. Now, you have reflexive Banach space. What about even smaller family of Banach spaces, what we call superreflexive? So what is superreflexive? Superreflexive, according to Gilles Pizier, there is a formal definition, okay, using ultra powers. But there is another way that you can see is you have an equivalent norm which is uniformly convex. A superreflexive means you have an equivalent norm which is uniformly convex. Keep in mind, for the fixed point property, once you change the norm, you may not prove that you have the fixed point property. It's really proper to the norm, okay? Now, the last one. Okay, fine. Forget about superreflexive. Forget about reflexive. What about L2? Okay? Can we prove that any equivalent norm in little L2, Hilbert, has the fixed point property? Still open. The one I showed you is a special equivalent norm, not any equivalent norm. So the Spanish people, the group of Garcia Falset and Enrique, they worked on this problem. They worked for years. And they are able to prove some stuff. The distance between Banach spaces, the Banach Mazur distance, and they proved something about this. Something. But the problem is still open. I think I'm almost done. Yeah, I'm done.
Thank you very much for this important talk. And of course, this is one of the toughest and important research area in fixed point theory.
Yeah.
Very important.
Yeah.
Resolving property